Okay, I am turning on the tape, so we are officially in business here today. And are you done? Oh, that doesn't care, but okay, so we are begun, as I mentioned here. I have posted for you as usual there homeworks, right? So you do have a homework due this evening, this very short homework on more trigonometric graphs. So remember, you're really going to be relying on using either the computer to make the graphs with the link that's at the top of the homework, right? You may have to open the instructions, or at the top of the homework, there's the link to the Desmo screen that will allow you to construct these trigonometric graphs, or your graphic calculator, right? But otherwise, this is a really short assignment. And then a little bit longer is about inverse trig functions, which we are still really talking about, because we're talking about today more applications of inverse trig functions, mainly using inverse trig functions to help us solve equations. And so we'll finish those notes today. So this is a new homework that I have posted. Of course, the big news today is the tests are graded, right? So I posted the grades actually on Friday in WebAssign, so you know your grade, and then you can have your test back. But I think everyone here I've given the test back to. Okay, so for you guys online, your grade is posted, so you'll have to come to class if you want to pick up your graded test. The answers are now posted. Okay, so on Blackboard, under the there's a folder there in the Blackboard page that says test answers. That's where the test number 1 answers were posted, and the test number 2 answers are posted there now also. So you can look at actually what the answers were to the test. That's really more helpful if you have a copy of your test. So I encourage you to come here to class and get a copy of your graded test. So a lot of you now improved your score, so that's a great thing. So I'm very pleased by that. So if you're one of the people who improved your score, and in some cases, some people improved their score dramatically. So that's really a hopeful sign, right? Coming here to the close of the semester. And now what that means is that, you know, if you passed, right, if you got a 70 above, then you are eligible again to attend class on Zoom, right? So so you can start attending on Zoom. But however, I would caution you, I still think it's better for you to come to class. So if you if coming to class helped you improve your score on the second test, so so you don't want to fall back into bad habits that maybe led to a not a good score on the first test, right? If you had then improved your score on the second test. So so be careful of that. However, we'll stick to the agreement. The agreement is if you pass a test, right, then you can attend on Zoom, and that will count you as, you know, as having attended, right? If you're on my Zoom report as having attended. Okay. Now, on the other hand, some of you still did not pass test number 2, so you need to be coming to class, right? Okay, so so come to class. Now, one other thing that I have to nag at you about. Some of you have done well on the tests, but you're not participating in the homework very well. So that is dragging down your average, right? Your course average. So you can see your course average, right, in WebAssign. It's right there under my total. Of course, my total is really low, but your total is going to be higher than this. However, you don't want to be in a position of, you know, having a total grade that should be passing, or, you know, maybe a B, or maybe an A, except for you're not participating in the homework. All right. So we still have, several homework assignments left, several of which are posted there, right? And more to go before the end of the semester. So if you have not been participating in the homework and that is dragging down your average, then you need to start participating in the homework, because you really don't want to be in a position of passing the test, but then not making a good grade in the class because you didn't do the homework. Okay, that would be tragic. But however your average comes out on the syllabus, the way it's calculated according to the syllabus, that's what letter grade you're going to get, because that's what's published in the syllabus. So I have to go with that. So what the solution to the problem is, right? You got to start doing your homework. If you have not been doing your homework, you got to start doing your homework. That's obvious, right? But got to say it here once here officially in class, just to remind you of these things. Okay. All right. Do y'all have any questions about the test or grading or something? Not about your specific, not about how I marked your specific paper, but if you have questions about that, you can see me after class. But just in general, questions about grades and so forth. Okay, all right. So we're going to start the notes here in a second. We're going to still have to give some of the tests. Anybody else come in? I was on video. What's up, I did? Okay, so don't forget that more trigonometric graphs homework is due tonight, right? Okay, let me switch to the notes here. Some of these problems in these notes today are going to be a little bit complicated, so pay attention here. The first one, not so bad, the first couple, but then after this, there are some more challenging examples. All right, so what we were doing right before the test, if you can recall, is we were solving equations involving trigonometric functions, right? So these first examples are the form of the equation is really straightforward, but remember, solving these equations that involve trigonometric functions, if you want to find all the solutions to the equation, which is traditionally what's meant when you're told to solve an equation, that means find all the solutions to the equation. In some cases, though, you may be given instructions that just find some solution to the equation. That's sufficient. But in most cases, if the instruction just says solve the equation in mathematics, that means finds all the solutions. So what we're trying to do here in these examples is find all the solutions to the given equation. And since these equations involve trig functions and trig functions are periodic, right? They repeat values, right? Constantly, then it becomes challenging to find all the solutions to the equation because there's lots of them. Infinitely many, typically, right? So that's the hard part of really of solving these trig equations. All right. So I'm looking at example E here, but I want to, so that's the real example E. But since we haven't done this since before the test, let's start with a little bit simpler problem, although it looks like it's harder. It's really simple. But let's look at solving this equation. Cosine of X is equal to square root of 3 over 2. You can you can really solve that one by inspection, right? Okay. When I say solve an equation by inspection, you can just, you can just look at the equation and just based on your knowledge of trig functions, you can figure out what the solution has to be here, right? See, this equation is asking you for what's an angle X such that its cosine is square root of 3 over 2, right? So that's going to be a special angle, and so you can just rely on your knowledge of special angles to figure out what X has to be here, right? Or what one solution to this equation has to be here, right? What's an angle whose cosine is square root of 3 over 2? What's the first one you think of? Pi over 6, right? Yeah, right. Okay. So pi over 6, its cosine is square root of 3 over 2. So we know a solution to this equation has to be pi over 6, right? Okay, so we can easily, again, by inspection, come up with one solution to this equation. Now, formally, here's how we would go about solving this equation, not by inspection. All right, what we would do here is since we want to free this s from the cosine, right? We have to find some way of undoing that cosine function. And how do we undo functions? So what's the mechanism we've set up to cancel or reverse or undo functions, so to speak? Yeah, you apply their inverse, right? That's the purpose of inverse functions. So what we would do here is on both sides of the equation, we would apply the inverse of the cosine, right? Okay, and you would end up with this equation, correct? And now we know that cosine inverse and cosine, when we compose them like we are on the left-hand side of this equation, they cancel each other, right? And we just get x. So we get x is the inverse cosine of square root of 3 over 2. But now we're back to sort of the same situation we were at the beginning. We have to think of, oh, all right, what's an angle? Cosine is square root of 3 over 2. And so again, we have to rely on our knowledge of special angles, right? To see that, oh, x has to be pi over 6, right? But now remember, you have to be careful when you're evaluating inverse cosine, right? Because remember, the range is restricted, correct? So the size of the angles you're going to get from inverse cosine is restricted. So do you recall now from before the test? What size angles will you get from inverse cosine? 0 to pi. Yeah, that's correct. Remember, for inverse sine, it's minus pi over 2 to pi over 2. But for inverse cosine, it's 0 to pi. Well, pi over 6, though, is between 0 and pi, right? So this looks like it's perfectly okay. All right. So we know, as we already knew before, right? One solution to this equation is pi over 6. Now, the hard part here is finding all the other solutions to the equation. All right. A bunch of solutions you can generate easily from the pi over 6. So you can start with the pi over 6. And remember then, since pi over 6 is since cosine is periodic, right? And it repeats values every 2 pi units, the period of cosine is 2 pi, right? Then you know that every 2 pi units, either before or after pi over 6, you're going to get another solution to the equation. So the way you write that down, as we were showing last time, right, is you just write, we have solutions that are pi over 6 plus or minus some multiple of 2 pi. The k here is 1, 2, 3. So pi over 6 plus 1 times 2 pi, pi over 6 plus 2 times 2 pi, pi over 6 plus 3 times 2 pi, or minus pi over 6 minus 1 times 2 pi, minus 2 times 2 pi, minus 3 times 2 pi, etc. All of those numbers, whatever they turn out to be solutions to the equation. Now, in your homework for this section, that's the homework I just posted. When you're typing in your answers, like this one, where you have lots of solutions to an equation, you don't need to write the plus or minus, just plus. So I'm going to take off the minus here. The book just assumes that the k, that number k, can be positive or negative. If it's negative, then you're going to have pi over 6 minus some multiple of 2 pi. Yeah, Chad. Okay, for sine and for sine, it's, do you remember for sine? For inverse sine, I mean, it's minus pi over 2 to pi over 2, right? For inverse cosine, it's 0 to pi. And then all the other ones are just repeats of those two. So you just have to remember tricks to recall which it is. So for tangent, Jad, the way I remember this is tangent is sine over cosine. So you take the range of the inverse sine is the range of the inverse tangent. So that's minus pi over 2 to pi over 2. Does that make sense? But cotangent is cosine over sine. So we don't use it very much, but the range of the inverse cotangent is cosine, inverse cosine's range, which is 0 to pi. What about, then you can figure out the other one. What about secant? So secant is 1 over what? what now? 1 over cosine. So you use cosine inverse, which is 0 to pi. So for secant inverse, its range is the same as cosine inverse range, which is 0 to pi. Cosecant is 1 over the sine. So the range of the inverse cosecant, a function that we don't encounter very often, the range of the inverse cosecant is the same as the range of the inverse sine, which is 0 to pi. Okay. So there's really only two ranges you have to remember. The rest of them you can reconstruct. 0 to pi, which is inverse cosine, minus pi over 2 to pi over 2, which is inverse sine. Okay. All right. Now, that is one set of solutions. But when you're solving equations involving cosine or sine, you're going to get a second set of solutions. All right. Those are the ones you have to look for. All right. So this is kind of the complicated part. Here's what we have to think of. I need to find another angle between 0 and 2 pi, another angle between 0 and 2 pi, right, whose cosine also is pi over 6, whose cosine also is square root of 3 over 2. Okay, so I need another angle separate from this one, whose cosine is square root of 3 over 2. Look, so you know its reference angle has to be pi over 6, right? The reference angle has to be pi over 6. Now, we've already used pi over 6 itself, so we need another angle whose reference angle is pi over 6. What'd you say there? 11, it wouldn't be 11 pi over 12. That reference angle would be pi over 12, wouldn't it? No, no. Yes, that reference angle would be pi over 12. Yeah, you want to think it's 6. So you got the right idea, though. 5 pi over 6. Yeah. See what Jad is saying? I need another angle whose reference angle is pi over 6. So that could be in the second quadrant, right? So that angle would look like this, because I want its reference angle. I want its reference angle to be pi over 6. So so what's that angle that I drew? Well, it's not pi over 6. That's the reference angle. The angle is this one, which Jad concluded correctly was 5 pi over 6. So there's the other possibility. Now you might say, oh, well, what about over here in the third quadrant? There's an angle in the third quadrant whose reference angle is pi over 6. And there's an angle also in the fourth quadrant whose reference angle is pi over 6. Why not use those two? But the problem is, oh no, did I get the right one? Oh, I didn't get the right. It's is 5 pi over 6 the right angle to use here as the second solution? Yeah, because the cosine of 5 pi over 6 is what, Jad? You just said it. Yeah, in the second and the third quadrant, cosine is negative, but I want cosine to be positive square root of 3 over 2. Oh, so this is not the right angle, but we have the right idea. That's okay. All right. We still want an angle whose reference angle is pi over 6, but I've got to get it in the right quadrant. So what quadrant is it going to have to be in? 4, right. I've already used the 1 in 1, right? So it's got to be this one whose reference angle is pi over 6. Oh, okay. What's that angle? Let me draw that one. It's this angle. What's this one? 11 pi over 6, right? Is that what you said? Yeah, 11 pi over 6, right. Almost 2 pi, right? 12 pi over 6 is 2 pi. So we're just pi over 6 short of that. It's 11 pi over 6. And cosine is positive in the fourth quadrant, so I know that the cosine of 11 pi over 6 is square root of 3 over 2. Oh, so there's the other. This is called a basic solution. Pi over 6 is one of the basic solutions. Here's the second basic solution, but you get other solutions again by adding in multiples of 2 pi. So there they all are. See, they're thousands of solutions, right? Infinitely many solutions, but they're all pi over 6 plus a multiple of 2 pi, and then or 11 pi over 6 plus a multiple of 2 pi. All right, now okay, so that was the warm up. All right, so now let's try something that's a little bit harder. Let's try this one. All right, so I don't know. All right, so I cannot solve this one by inspection, folks, because I don't know an angle whose cosine is 0.65. Okay, I'm not that good. 0.65 is not, this is not going to be one of our special angles, right? Okay, so how am I going to go about solving this equation? I can't solve this one by inspection. So you do have to use kind of your formal approach here. All right, apply. So I'm going to erase this. Are you going to get mad if I erase this? So I'm going to erase this. But what I'm getting ready to write down looks a lot like this. Because we're going to solve this in a very similar fashion. All right, so apply inverse cosine to both sides. Right? So inverse cosine of 0.65. On the left-hand side here, that's the easy part. You get x. Now we have to compute the inverse cosine of 0.65. I cannot do that by inspection, but that's actually good, right? Here I can use the calculator. So you're going to have to use the calculator here. Find the inverse cosine of 0.65. Make sure you are in radian mode. It's not the end of the world if you're in degree modes, but we want our solutions in radians here, so not in degrees. So let me try switching to radian mode. And then let me see, where is inverse cosine on my calculator? I found it. So that took a long time to compute. I get approximately, you're going to have to round off a little bit. I'm going to round off to a couple of decimal places here. I have 0.86. All right. So here it is. In this picture, there is, I'm going to use the same picture. There is, I claim, 0.86. All right. Really, here's where it's really helpful in degrees. What is 0.86 in degrees? I'll do that. Multiply by 180 over pi, remember? About 50 degrees, is that what y'all are getting? Did y'all try that? Yeah, yeah. So close to 50 degrees, right? So so x there is about 0.86 radians, which is close to 50 degrees. So my picture is a little bit off. This angle is going to be a little bit more than 45 degrees. Okay, but that's good enough for what I'm doing here. All right, so there's one solution, 0.86 radians, and then again, just add on multiple of 2 pi. So there you get infinitely many more solutions, right? By just adding on a multiple of 2 pi. Now, the hard part is you have to find, that's one basic solution. You have to find the other basic solution. But it's going to look much like this, right? Where is that other angle going to be? Since the cosine has to be positive, the second basic solution has to be where? Yeah, just like in this picture, right? It's got to be in the fourth quadrant. And its reference angle has to be 0.86. So if you draw it, let's pretend that I've drawn it there. And so this angle is not pi over 6, like it was in the previous example. This reference angle is 0.86. This angle is 0.86. So what is the full angle? Yeah, 2 pi minus 0.86, right? Because one full revolution would be 2 pi. So subtract off the 0.86 to get your angle. So it's not 11 pi over 6 anymore. It's close to that, though. It's 2 pi minus 0.86 approximately, which is, how much is 2 pi minus 0.86? 5.42. I think that is right. Sounds right to me. So about 5.42 radians plus, again, any radians plus, again, any multiple of 2 pi, okay? So is that kind of making sense to you? That looks ugly, right? Yeah. When you're not using special angles, things get really messy, except the good thing is you get to use your calculator, right? Okay. So you can use your calculator to compute these inverse trig functions instead of having to do that in your head. All right, let's try the next one then. The nice thing about the next one is for tangent and also for cotangent, you only need one solution. You only need one solution. You do not need two basic solutions. Okay, you only need one. So remember that for tangent and cotangent as well, one solution is all you need. And then you're going to add on a multiple of pi, not 2 pi. Okay, just pi. All right. So because the period of the tangent function is pi, not 2 pi. So so let's see if we can figure this one out. So apply inverse tangent to both sides to undo the tangent function. And so we get theta is equal to the inverse tangent of 1. So we're thinking, what angle has a tangent of 1? What does your calculator say? 45 degrees in degrees, 45 degrees, which in radians is what? No, that's the that's the sine and cosine of 45 degrees, pi over 4, right? Yeah. So the theta here is pi over 4 in radians. 45 degrees, which is that's what the calculator says, and but that's pi over 4 in radians. So there's our radian solution. It's pi over 4, and then now it's easy. You just have to add on a multiple of pi, just a multiple of pi. And that's it. So it's easier, I think, solving equations with tangent because you don't have to look for that second basic solution. Now, fortunately, in applications, as you're going to see in a moment here, in applications when you're solving trig functions, in applications like word problems, usually you're not interested in infinitely many solutions to a word problem. You just want one solution. Okay, so so it's in applications, solving trig equations is not as complicated as it is in these abstract settings. All right, I'm going to let y'all try one now. Now this is one where you'll need your calculator. Okay. Camille, it's easy. All right, okay. So we have whichever. Oh, what about H? Oh, that was scaring you? You look like you're about to cry. All right, well, hang on. All right, that one is kind of, there may be some tears shed there, I admit, but we'll do that. Okay. All right, so y'all try this one. Tangent of theta is 2. You need your calculator here because this is not a special angle. Okay, so you need your calculator. Try to put it in radian mode. It really doesn't matter if it's in radian mode here at all, because once you get the solution, do the same thing that we did in this prior example. So it's really just the answer is really just kind of a number 2. Don't really. I left room here for drawing a picture, but you don't need to draw a picture. Not necessary. You guys at home also. So you need your calculator here for sure. Oh, where did I get the 2 from? Nowhere. This is just a problem. Just made it up. There's nothing special about it. Yes. No, try to give it in radians. That sounds a lot like degrees. Yeah, okay. So if you get it in degrees, then you can type in the numbers again, or you can just take the 63 and multiply it by 180 over pi, right? And convert it back to radians. Let me. But if you're struggling with the radians, no, you can work in degrees, but then remember to convert the degrees to radians before you give your answer, right? Okay. Oh, okay. But your phone will switch to radians, one. Oh, okay. Okay, let's try this one. So y'all can just tell me what I need to do. So formally, what's the first step here? Yeah, use inverse tangent, right? So just like in the prior example, apply inverse tangent to both sides, right? And now here's where the calculator becomes essential, because only the calculator knows what the inverse tangent of 2 is, right? The inverse tangent of the tangent of theta is theta, but only the calculator knows what the inverse tangent of 2 is. And so in radians, what does, see what my calculator says, it's very slow computing that, which is interesting. I get about 1 point, I'm rounding off, so about 1.11. All right, so there is our basic solution, 1.11. And so that's kind of like the smallest positive angle that's the solution here. And then you get more solutions just by adding on multiples of pi, not 2 pi, but just pi. So just pi for tangent. That's it. So see, that's really easy problem. Okay, so the calculator makes that one easy for us. Ooh, let's check that one. So let's add on a multiple of pi here to this. So pi is about 3.14, right? So if I add that, so 1 pi is about 3.14. So if I add on 1 pi to 1.11, I'm going to get 4.25 about, right? 3.14 plus 1.11 is 4.25. So our second solution, second positive solution is 4.25. Let's see what the calculator says. The tangent of 4.25 is, hopefully it'll be close to 2. I didn't, oh, I'm already in. It is 2. Yeah, this thing switched back to degrees on me.
Do you need 2 solutions for this problem? Just one, since it is tangent.
No, you only need this one solution. That's all. And then just add on a multiple of pi. I just was wondering, what is 1.11 plus 1 times pi? Because that's supposed to be another solution, right? That's about 4.25. I just was checking that with the calculator. And indeed, the tangent of 4.25 is almost 2. Okay, so so our recipe here for more solutions seems like it might be correct, right? 1.11 plus a multiple of pi. But that's just an experiment. You don't need this. This is the that's the answer. Okay, now as Emil is pointing out, the next example looks terrible. So this looks and it is kind of hard, all right? Because it's going to be combining now 2 ideas for us. Well, actually multiple ideas, but 2 key ideas here. One from algebra, and then of course the trigonometry, because that's obviously an equation that involves trigonometry, right? We've got this equation, kind of complicated and set equal to 0, and we want to see if we can find the solutions to this equation. First, think of this. Think of the form of this equation. You have 2 times this quantity squared minus 7 times this same quantity, the quantity being cosine theta, right? Remember, this means cosine theta and squared, right? Not cosine of theta squared, but cosine of theta, and then squaring that quantity. So you have 2 times this quantity squared minus 7 times the same quantity plus 3 is equal to 0. If you wrote that, like you do in college algebra, say, well, I have 2 times some quantity squared, but I'm going to call the quantity x in algebra, right, instead of cosine theta, minus 7 times that same quantity, which I'm calling x, plus 3 is equal to 0. See, if you kind of rewrite that equation as you would in a college algebra class, you get an equation that looks like this, right? Okay, here we're letting x be our mystery quantity. Here the mystery quantity is cosine theta. But in algebra, all unknowns are usually labeled x, right? So you would have an equation like 2x squared minus 7x plus 3 is equal to 0. Now, the reason I wrote that equation as you would in an algebra class is you're very good at solving equations from algebra. How would you try to solve this equation? What technique would you use? It's the F word. Factoring, right? Yeah, you would factor. Okay, so how does this factor? In fact, or does it factor? If it doesn't factor, then we're really in the soup, right? But see if it will factor. So it's got to be something like 2x times x, right? That's the only way you'll get the 2x squared. And then to get a product of 3, it's got to be 1 times 3. But I got to make sure I get the 1 in the right spot. Looks to me like the 3 would go here, so I can multiply it by the 2x. That would be 6x. And then the 1 would go here, right? Because 6x plus another 1x would be 7x. And what about the signs? They both have to be negative, correct? Because I've got to get negative 7x. Oh, so that does factor. You can check it. That's correct. So this factors as 2x minus 1 times x minus 3 equals 0. Now you're on your way, right? What do? Take both of your factors and do what? Yeah, you set them to 0, and then you solve those 2 equations. But those are really easy equations to solve, right? So we can see in algebra, right? That gives us a glimpse here of how to solve this equation. We're going to factor. So this equation will factor as 2 times cosine of theta. See, cosine of theta is x, right? 2 times cosine of theta minus 1 times cosine of theta minus 3 equal 0. Just check that and multiply it back together, see what you get. 2 cosine theta times cosine theta, that's 2 cosine squared theta, right? 2 cosine theta times minus 3, that's minus 6 cosine theta. And then minus 1 times cosine theta is another minus cosine theta. So you have minus 6 cosine theta minus 1 cosine theta. That's minus 7 cosine theta. That's right. And so minus 1 times minus 3 is plus 3. So see, there we have it factored. And now you set the factors to 0, just like you do in algebra. So you get 2 cosine of theta minus 1 is equal to 0, or cosine of theta minus 3 is equal to 0. And now let's solve those 2 equations. I'm going to start with the second one first, because this one is very easy to solve. If you take the minus 3 to the right-hand side, you get cosine of theta is equal to 3. Look, if you take cosine of an angle, think about cosine function. If you take cosine of an angle, how big does that get? What's the biggest cosine can be? What now? No, think about, Jad, think about the graph of the cosine function. Goes up and 1, right? The biggest the cosine can get is 1, right? It never gets bigger than 1, correct? What's the smallest it gets, Jad? Nope. You can have negative cosines, right? But what's the smallest number you can get as a cosine? -1. Yeah. So cosine always fluctuates between -1 and 1, right? But it never gets to 3. So what's the solution to this equation? Undefined, right? There are no solutions to this equation, right? Now, if you didn't realize, oh, cosine of theta cannot be 3, how would you try to solve this? You would put the inverse cosine on both sides, right? And then you would say, I don't know any angle whose cosine is 3, so I'll have to use my calculator. And then you use your calculator to compute inverse cosine of 3. What does it say? Error? Yeah, right. Okay, you can't do that. Make sure you're in radian mode though. Because if you take the inverse cosine of 3 degrees, you'll get a number. It's going to be very close to 1. There are no solutions here. So, oh, yay. All right. So that one we can just throw away. That didn't help us at all. And now let's try this side. So maybe we'll get no solutions here. And that just means the original equation had no solutions, which is certainly a possibility. Just because you write down an equation doesn't mean it has to have solutions. Let's write down. Let's move the -1 to the -1 to the right-hand side. So that becomes 2 cosine theta is equal to 1. And then divide both sides by 2, right? And now you have cosine theta equals 1/2. Ooh, that looks a lot more familiar to me. So now I have to think here, well, apply the inverse cosine to both sides, right? Right. Apply the inverse cosine to both sides. And so I get theta is the inverse cosine of 1/2. In other words, I need an angle whose cosine is 1/2. What's the first one you think of? Pi over 3, exactly. So we have this solution up here, pi over 3. Great. So I know one of my answers here is pi over 3 and then plus, right? Any multiple of 2 pi. So you get a lot of solutions that way, but this is cosine, so you have to find the second basic solution. Where is the second basic solution going to live? Remember, we want cosine to be positive 1/2, fourth quadrant, and the reference angle has to be the same as pi over 3, right? The reference angle has to be pi over 3. So what is it? So what angle in the fourth quadrant has reference angle pi over 3? Close. 7 pi over 3 is a little 7 over 3 is a little bit bigger than 2, Emil. So you went a little bit over 5 pi over 3, right? You went to one, you went a little bit over, Emil, but we want to be a little bit under. It's actually 5 pi over 3. That's the right angle, correct? 5 pi over 3 plus another pi over 3 with 6 pi over 3, that's 2 pi, right? So there's the other possibility. By the way, I think you could have used a negative here. I think you could have written minus pi over 3. I think that would also work. So you get, there's your other possibilities there. 5 pi over 3 plus a multiple of 2 pi. Okay, let's try this another one like this. More complicated equation equals 0. So again, you're going to use factoring. All right, so you want to see if you can factor that left-hand side of that equation. Going to have some factoring involving sines or cosines or maybe some numbers. Can you factor the left-hand side of that equation? Try that first and see if y'all can tell me what the factorization is, and then we'll go from there. All right, so see if you can factor something out of some way. You can factor 5 sine theta cosine theta plus 4 cosine theta. Just once you get it factored, just stop there and then we'll. Solution. Okay, were y'all able to factor something out of this left-hand side of this equation? What factors out, Jed? Cosine, yeah, you have cosine in both terms, right? Here you have 5 sine theta times cosine of theta, right? And then here you have 4 cosine of theta. So that means you can factor out from both sides, I mean, from both terms, a cosine of theta. So factor that out. I don't think you can factor anything out of the coefficients here, 5 and 4, right? There's nothing other than 1 that divides into 5 and 4. But you can factor out a cosine of theta, and that would leave you with 5 sine of theta, right? Because we factored out the cosine. And then here you're just left with a 4. And now you have that, but you got this right where you want it because you have a product that equals 0. This is something other than 0. You're still in bad shape, but here you have a product equals 0. So that means one of the factors is 0. And that's all we need to know. So we have cosine of theta is 0 or 5 sine of theta plus 4 is equal to 0. And now you just start working on these two equations separately. They're a little bit simpler, right? Cosine of theta equal 0. You can solve that one so easily, I think. But let's go through the steps. So we apply inverse cosine to both sides, right? Remember, this is 0 on the right-hand side, not theta. And so you get theta is equal to the inverse cosine of 0. So what angle, we just have to think about this ourselves, right? What angle has cosine 0? So that is a special angle. It's not 0, because cosine of 0 is 1. Pi over 2. Yeah, pi over 2 is the first angle that has cosine of 0. Remember, cosine starts at 1 and then goes down to 0 at pi over 2, and then goes down to -1 at pi. Okay, so there's one solution, pi over 2, and then add on your multiples of 2 pi. Now, this being cosine, however, we have to find the second basic solution. So what's the other angle between 0 and 2 pi whose cosine is 0? 3 pi over 2. The other one is 3 pi over 2, right? Remember, cosine, it starts at 0, goes to 0, goes down to -1, and then comes back up to 0 at 3 pi over 2. And then when you get to 2 pi, of course, it's back at 1. So the other possibility here is 3 pi over 2. And then add on multiples of 2 pi. All right, wow, there's a lot of solutions already. And we're just halfway through solving the equation. We've got all those solutions already as solutions to the equation. Now we have to work on this equation. So let's see, I think I would take the 4 to the right-hand side, right? So I'd have 5 sine of theta is -4, and then divide by 5. So we have sine of theta is -4/5. So I feel the calculator going to be useful here, right? Because I don't know an angle whose sine is -4/5. Well, let's apply the inverse sine to both sides. And when you do that, I'm going to skip a step here, but when you apply the inverse sine to both sides, you'll get theta is the inverse sine of -4/5. That is your first solution. So what's your calculator going to tell you that is? You're going to have to rely on the calculator. All right. So what does it say? -0.93. So that is down in the fourth quadrant. If you convert that, what is that in degrees, by the way? Really helps to. -53.13. Yeah, so I didn't draw that too bad. Okay, -53.13, a little bit below -45 degrees, right? Okay, so there's the picture of one of our solutions there, right? Is -0.93, right? Radians plus some multiple of 2 pi. So there's a bunch of solutions. Sadly, that's not all of them, however. Okay, all right. Because now, since this is sine, we have to find another basic solution, and again, add on multiple 2 pi. Where is that other basic solution going to be? Remember, your sine is negative. So where is sine negative? It's negative over here in the fourth quadrant. We already found this one. So where's the other possible answer? Third quadrant. It's got to be in the third quadrant, right? Got to be in the third quadrant, and its reference angle has to be the same as this one's reference angle. Well, that reference angle is 0.93. Positive 0.93. Okay, so you're 0.93 into the third quadrant. Just like this angle was 0.93 into the fourth quadrant, right? So what's the full angle then? You draw it, looks like this. What's that? What's that full angle? Yeah, it's just the 180 degrees, which is pi, right? Plus another 0.93, right? So you have pi plus 0.93. How much is that approximately? Oh, 2.21. Yeah. So about 2.21 pi. No, is this right? Yeah. Yeah. I thought that was all right. Yeah. 4.07. That sounds better. What'd you do wrong there, Fernando? Oh, okay. All right. So 4.07. Yeah, that's going to be an easy mistake to make. But remember, the reference angle has to be positive. So it's 0.93 plus that extra pi. So 4.07 plus, again, a multiple of 2 pi. Well, that one's pretty tough, right? That's about as hard as they get, I think, solving these trig equations. So you get all kinds of solutions here, right? That's going to be challenging just to type into WebAssign all of those solutions. Now, you won't use parentheses. You may have to separate with commas. So you might have pi over 2 plus k times 2 pi comma. What was that other thing? 3 pi over 2 plus k times 2 pi comma, etc. Have to read the instructions really carefully. But you don't have to write plus or minus, and you do write k times 2 pi. That's how it shows the answers. Okay. Well, let's let's apply some of this knowledge of solving trig equations, and we're going to go back to one of our favorite things that we already know how to do pretty well, and that is solve triangles. So we learned, and you showed me that on the test, how to find the lengths of sides, right, or the size of angles, right, in right triangles, given some information about the right triangle, correct? Okay, so that process is called solving the right triangle. But actually, we can solve other triangles as well. Okay, so now we have enough knowledge to be able to find the lengths of sides or the size of angles for any triangle or almost any triangle. All right, not just right triangles. And we're going to use now to do this a generalization of the Pythagorean theorem. So we know our good old Pythagorean theorem, right? Tells us that in a right triangle, right, we have this relationship between the lengths of the sides, correct? That's for a right triangle. But it turns out that there's a similar formula to the Pythagorean theorem for any triangle. And this formula is called the law of cosines. All right. So let me show you the way the law of cosines works. Suppose that you have just any old triangle, any triangle at all. And we're going to label the angles in that triangle. So remember, this does not have to be a right triangle. We're going to label the angles in that triangle with capital A, B, C. All right. For the purposes of this picture. And then the side opposite an angle, we're going to label that with the lowercase version of the same letter. So you see how this is done. Since this is angle capital A, this side opposite of capital A, I'm going to call that lowercase a. All right. And then since this is angle capital B, the side opposite of that, I'm going to label that lowercase b. Since this is angle C, I'm going to label the side opposite of that lowercase c. So I did the same thing in this right triangle here. I labeled these two angles, capital A and capital B. And the right angle, I labeled it as capital C. Okay. All right. So here's what, all right, that's just the setup. Okay. So imagine you have a triangle and your sides are labeled like this. All right. So what the law of cosine says is the following. Okay. Let me start with the third version of the law of cosines, but these are really all similar, right? What the law of cosine says is, okay, the length of this side C, if you square that, that's going to be equal to the sums of the squares of the other two sides, right? Minus, but you have to subtract something off then, because this is not a right triangle. You have to subtract something off. And what you subtract off is 2 times the product of those other two sides minus the cosine of the angle, opposite side C. All right. All right. So let's look at that. Again, here's our triangle, right? So what the law of cosine says is, okay, the length of this side squared is going to be the square of these two lengths added together. So that's like the Pythagorean theorem, right? C squared is A squared plus B squared, but we have to subtract off something now. Twice, 2 times this side minus the cosine of this angle. Make sure you take the cosine of the proper angle here. All right. So since we were trying to find the length of side C, lowercase c here, we had to subtract off 2 times the product of these two lengths minus the cosine of this angle opposite C. Now, you can do the same thing for the other sides as well. So if you wanted to know the length of side A, what the law of cosine says is, okay, A squared, not just A, but A squared is going to be B squared plus C squared minus 2 times B times C times the cosine of this angle, the side opposite lowercase a. What about for B? for B, the law of cosine says, okay, B squared is going to be A squared plus C squared minus 2 times A times C times the cosine of this angle opposite lowercase b. By the way, the law of cosines applies to any triangle at all. So it also applies to right triangle. So look in a right triangle, what happens if you apply the law of cosines? Suppose we wanted to find the length of C, right? Okay, which is the hypotenuse here. According to the law of cosines, that would be what? Well, we would take what? A squared, right? Plus B squared. But what would we have to subtract off? 2 what? AB times the cosine of C. But what's C here in a right triangle? It's 90 degrees. It would be 0, right? The cosine of 90 degrees is 0. So this last term would drop out, you see, and you would just get your familiar Pythagorean theorem, which is just C squared is equal to A squared plus B squared. What now? No, 2AB cosine 90 degrees, right? Yeah, it's C squared is this squared plus this squared. This is, I'm using the law of cosines here, right? Okay, so C squared is B squared plus A squared minus 2 times A times B times the cosine of the angle opposite C. But that's 90 degrees in a right triangle. So that becomes 0. And so you get the Pythagorean theorem. So the law of cosines is, it's a generalization of the Pythagorean theorem. It's more powerful than the Pythagorean theorem. The Pythagorean theorem is just a case, a special case of the law of cosines. Well, let's try it there. We'll put it in an actual application. This is how it would actually be used. Okay, so let's see. A tunnel is being built through a mountain. Okay. Have y'all seen the tunnels that they built along Memorial Park? Yeah. Except there, they built a mountain over the tunnel. All right. So the tunnel came first and the mountain came second. All right. So here, the mountain is there and we're going to build a tunnel through it, right? So a surveyor makes the following measurements. Okay. So a surveyor goes with surveying instruments and surveys from this particular point, okay, away from the mountain, the distance to the left-hand side there of the mountain was 388 feet. The distance to the right-hand side was 212 feet. And then this angle, right, separating the two sides was 82.4 degrees. We want to know what's the length of the tunnel. Okay, so what's the length of the tunnel? So say we don't have any guarantees that anything in this picture is a right angle, right? So we really can't use our straightforward right angle trigonometry, but that's okay. We can use maybe the law of cosines, right? So how shall we label things? Well, all right. So first you want to label your angles. Okay. So I'm going to label the angles capital A, capital B, capital C, just to match up with the law of cosines. And this angle just happens to get labeled C, right? So that means what's the correct label for this side opposite? Yeah, lowercase c, right? Okay, so these two sides, let's see, this side would be B, right? Opposite angle B, and this side would be lowercase a, opposite angle A in the picture. So according to the law of cosines, the length of this side squared, that's the length that I don't know, correct, is going to be, well, just to write it out fully first, A squared plus B squared minus 2AB times the cosine of C, right? But now we can fill in a lot of these values because we know them because the surveyor has measured them, right? A is what, 212? So you get 212 squared plus B is 388. So you get 388 squared minus 2 times the 212 times the 388 times the cosine of, and this angle is 82.4 0.4 degrees. So you do get to use degree mode here. That's nice. And so it's just a matter there of doing the calculations, and you'll know the value of C. Let's see what those calculations are. So what is C squared? Don't take the square root yet. So if you take 212 squared plus 388 squared minus 2 times 212 times 388 times the cosine of 82.4 degrees, I'll do all that at once there. What does that give you? Kind of a large number, I think. $173,730.24 for good measure there. The 0.24. Anyone else? Did y'all get, anyone else get that? 173,730.24. Square this, then subtract off this product. I need a confirmation or we need a dispute here to figure out what it is. Okay, so we do have a difference there. All right. So Ravi has a slightly different number. Anyone else got something? Let me let's write it down. So let me see what I get here, sort of. All right, so 212 squared. That should be pretty easy. Is that 44,944? 44,944 plus, and then 388 squared. 150,544. Okay. And now let's see what this is. So 2 times 212 times 388 is 164,512. But I haven't put in there yet the cosine of 82.4 degrees. All right, so I've got this. Oh, it is? Okay. Yeah, it looks like that's what I'm going to get too. All right. Yeah, 173,730.24. Yeah. Okay. That's what you add up these numbers. That's what you will get. So that's but that is C squared, right? So we want to take the square root of that, correct? All of this. So we get that C is going to be the square root of 173,730.24 approximately. So it looks like what C is going to be about 416.8 or 0.81 if we want 2 decimal places. Okay, so about 417 feet, right? Pretty close to 417 for that tunnel. See, that's pretty easy. Yeah, so we always have that problem, right? Don't mix up radians and degrees. Sure, I've got the date on this, right? Now, You can apply the law of cosines, though, in various ways. So let's try, see if we can figure out answer to this question. So here we want to find the angles. Here we want to find the angles in this triangle, not the lengths of the sides. Those are all given to us, right? So we got these simple lengths of these sides, 8, 5, and 12. But now we want to find the size of the angles. That also can come from the law of cosines. All right. Let me show you. You're gonna have to solve an equation, but let me show you the equation that you want to solve. All right. So again, we're looking for the size of angle A, right? So let's apply the law of cosines with the length of side A. All right, lowercase a, which is 5, right? Remember, the law of cosine says that lowercase a squared is equal to what? B squared plus C squared minus 2 times B times C times the cosine of what? A, right. And see, since we're looking for A, then if we write down this equation, we'll have an equation involving cosine of A, and then you might be able to solve that equation to find A, right? Okay. Now, you have to make sure you've only got one unknown in this equation, but that's true, correct? Because these three lengths of the sides, you're given all of those. So you can fill those in. Let's fill them in. We would have what? 5 squared is equal to 8 squared plus 12 squared minus 2 times, what did I just say there? 8 times 12 times the cosine, but see, we don't know A, but that's the only unknown. So we get 25 is equal to 64 plus 144 minus 2 times 8 times 12. 2 times 8 times 12, 192. Am I doing that right? Times the cosine of A. So let's move numbers around. Let's move the 64 to the left-hand side and the 144 also to the left-hand side. That leaves us on the right-hand side with minus, be careful, minus 192 times the cosine of A. Now, divide both sides by minus 192. Of course, you can add these numbers together as well, right? So what does that lead us to finally? I think it's, what is that going to be? You got what? Yeah, when you add these numbers together, what do you get? Minus 183 over minus 192 is the cosine of A. That we add those together, right? 25 minus 64 minus 144. Is that minus 183? I think so, yeah. So we have minus 183 on the left-hand side, and then we divide that by minus 192, right? So we can get rid of the minus 192. So we get cosine of capital A is minus 183 over minus 192. Of course, that's going to be positive, but it's going to be positive some little tiny number. Can you guys tell me now what A is? So how do you solve that equation for A? Apply what to both sides? Inverse cosine, sure, right. So you have inverse cosine of the cosine of capital A is the inverse cosine of, well, the minuses cancel. So you get whatever 183 over 192 is, right? But your calculator will do that for you very nicely. And you only care about one solution here, right? So you don't have to worry about multiple solutions. The first solution you find is going to be the one that you want. I would do it in degrees because I think it makes more sense in degrees. That's what I get. So my calculator says A is about 17.6 degrees. That picture doesn't look very accurate, does it? All right, well, let's stop there for a moment, but I'm going to ask you also to find B and C. Okay, all right, but the steps will be almost identical, right? Okay, except you'll be using a slightly different version of the law of cosines. Hopefully, when you find A, B, and C, they all add up to what? 180, because if they don't, something definitely has gone wrong, right? Because in any triangle, right triangle or otherwise, all the angles have to add up to 180. Okay, let's pause there for a moment and take a few minutes here. And y'all can play with this if you want to. Last two examples. So finding angle B, right, is going to be very similar to finding angle A, except you're just going to switch which version, right, of the law of cosines you're going to be using. So we'll use the one that's kind of centered on the side, will be right, because the law of cosine tells us that lowercase b squared is going to be lowercase a squared plus lowercase c squared, right, minus 2 times a times c times the cosine of that angle B that we're trying to find, right? And since we know the values of A, B, and C, lowercase a, B, and C, right, then the only unknown in this equation is cosine of that angle B, right? So we can solve for that and then use that information to figure out what B actually is. So filling in those values, right, again, just like in the prior example, let's see, we had 8 squared is equal to 5 squared plus 12 squared, right? And then minus 2 times 5 times 12 times that cosine of angle B. So 64 is equal to 25 plus 144 minus 120, 2 times 5 times 12 times the cosine of that angle B. And then let's just move our constants to the left-hand side, right? So so on the left-hand side we have, if I can squeeze it all in here, 64 minus 25 minus 144, right, is equal to minus 120 times the cosine of that angle B, right? Let's see, 64 minus 25 minus 144, what is that, minus 95 or something like that? Am I doing that right? Minus 105, missed by 10. So minus 105 is equal to minus 120 times the cosine of angle B, and then divide both sides by the minus 120. Of course, the negative signs are going to cancel. So we get 105 over 120 is equal to the cosine of angle B. And now just compute just like before, right? Just apply inverse cosine. And since 105 over 120 is not going to be a special angle cosine, right? We're definitely going to have to use our calculator to help us figure out what B actually is. The inverse cosine of 105 over 120. That also is going to be a small angle, isn't it? So C is the big angle here, right? What is that? 28.95. Yeah, so or well, All right, so yeah, let's just say 29 here, close enough. So B there is about 29 degrees. Now, that angle C, of course, you can figure that out also by using the law of cosines again, right? In exactly the same way. But now, since assuming that we have computed these two angles correctly, now we know since we know both of these angles, right, we can use what I mentioned before, right, that the three angles in a triangle have to add up to 180 to find out what C is, right? So just take 180 minus the 17.6, right? And then also minus the 29. And that should give us the size of angle C, right? Approximately. So C is going to be about whatever that is. 133.4. All right. There are some instances where you're trying to solve triangles and you will not be able to use either. You will not be able to use the law of cosines. You don't have the proper information for using the law of cosines or the Pythagorean theorem, which is really the same, right, as the law of cosines. There's one other law called the law of sines that we also can use to help us solve triangles. All right, but I'm not going to discuss right now sines. Okay, so there's a law of sines in addition to law of cosines, and it's also used to help solve triangles. So we're going to, as I mentioned here, we're going to let go of trig for a little while, but we're not going to let go of inverses yet, all right? Because we're going to mention another important pair of functions that are inverses to one another, but they're not trigonometric functions at all. Okay, and you may be familiar with these functions from algebra, because they're often discussed in an algebra class, but sometimes not. So the way these functions work is you take a base, which in this case is the number e. So this is a number, e is a constant, right? Okay, and you raise it to the input, whatever the input to the function is. All right. So notice that your variable x is located in the exponent in this formula. That's why these are called exponential functions. And you can also, of course, put a minus sign in the exponent as well. So another important exponential function is this base e raised to the minus x. Remember, e is a constant like pi. It's an irrational number. Its approximate value is 2.71828, but that's not its exact value because it's irrational. When you write out its decimal expansion, you get a non-repeating, non-terminating decimal. So notice I got the ... here. So this decimal expansion continues infinitely, and it doesn't ever repeat. Okay, so that in a sense that makes e a challenging number to work with, but it's of course it can find it on any calculator, right? Any scientific calculator will allow you to bring up here or use this irrational constant. These two functions now, where you take that base a and raise it to the x power, or you take the base e and raise it to the minus x power, these are called the natural exponential functions. And these play a really vital role in calculus for theoretical reasons, but also for practical reasons as well. Many quantities in nature can be modeled using exponential functions. the reason that is the case is I can explain it just a little bit. I can't give you a great explanation here, but I can explain it a little bit. By the way, here's the graph of the natural exponential function. So here's the graph of e to the x. Notice it's not a particularly interesting graph, right? So it's not a straight line, obviously, but you have a graph that looks like this. And here's the graph of e to the here's the graph of e to the minus x. Okay, and again, the reason that these play a vital role in applications, these functions play an important role in calculus for theoretical reasons, but in applications is, notice that the natural exponential function is increasing, right? It's growing. It's not growing at a steady rate, obviously, because if it were growing at a steady rate, what sort of curve would you get? A line, right? Okay, so exponential functions are increasing. The natural exponential function is increasing, but it does not increase at a steady rate. However, it does increase at a steady percentage rate. Okay, so it's if you compute its percentage growth rate, you'll get a constant, a steady number, right? So it's in a sense similar to linear functions, okay, but obviously the graph's not a straight line. And many quantities in reality, right? Many quantities in the real world have this property that they don't grow at a steady rate like lines, but they grow at a steady percentage rate. Okay, so that's why exponential functions are useful to help us model important real world quantities, those that grow at a steady percentage rate. You can form an exponential function, by the way, from any base. Okay, do not have to use base e, but for many reasons, base e turns out to be a very important base, even though the number e is this weird irrational number. Exponential functions with base e turn out to be the most useful or the most important. That's why these are called the natural exponential functions. But any base can be used to form an exponential function. So here's another important exponential function where you have base 2 raised to the power of x. That's called the binary exponential function. Or another important one is where you have the base 10 raised to the power of x. That's called the common exponential function. May be wondering what's so natural about having the base e that it's called natural exponential function. That's an interesting question. Okay, but actually, natural exponential functions were historically appear before other exponential functions do. Okay, so there is something that is natural in some sense about base e. Okay, for reasons that we're not going to go into. All right, let's look at some of the important features of the natural exponential function. You can discover most of these really easily. All right, so there's the natural exponential function e to the x power, not e to the minus x power. E to the minus x power is also called natural exponential function, but let's focus here on just e to the x. All right, to the positive x. All right, so first, what's the y-intercept? So where does the blue line is e to the x power? So where does that cross the y-axis? You can see it in the graph. Where is it? You'll see that right there. That's at 1, right? Okay, but so the y-intercept is equal to 1. But of course, how could you discover that if you weren't looking at the graph? How do you find the y-intercept of any function? Set x to 0, right? So the y-intercept you get by computing f of 0. So that would be e to the 0th power. And remember, whenever you raise a base to the 0th power, you always get 1 for any base, right? Okay, you always get 1. So actually, for any exponential function, whether it's the natural exponential function or the base 2, that's called the binary exponential function, or the base 10, that's called the common exponential function, they all have the same y-intercept. It's 1, because any base raised to the 0th power is going to be 1, with one exception. 0. If you raise 0 to the 0th power, that is undefined. Okay, you cannot raise 0 to the 0th power. It's like dividing by 0. You're not allowed to do that. So in arithmetic. So so the y-intercept is 1. Whereas increasing, you can see on the graph, it's always increasing. I mean, e to the x power is always increasing. E to the minus x power is always decreasing. So you don't get any turning points on the natural exponential functions. Okay, that it doesn't switch from increasing to decreasing or vice versa. E to the x is always increasing. E to the minus x is always decreasing. Also, you don't have any x-intercepts. So see, kind of boring in that sense. No x-intercepts at all for either of these two functions. The reason that's the case is you just have to use a little bit of your algebra and arithmetic knowledge. How do you find x-intercepts of a function? General, you set y to 0, right? So in other words, you set the formula to 0. So for the natural exponential function e to the x power, if we set that to 0 and then try to solve the equation, we have this equation to solve. And we can see by inspection that equation has no solutions. You cannot raise any base to a power other than you cannot raise any base other than 0, I should say, to a power and ever get 0. Any number other than 0 to a power is never 0. Okay, just think about that. Okay, cannot raise any base other than 0 to a power and ever get 0. That doesn't happen. So this equation has no solutions, which means you don't have any x-intercepts. E to the minus x also does that. Also have no solution either. Okay, so so no x-intercept. So kind of boring in that respect. What about the domain and range of, let's just look at e to the x power. Well, actually, both of them have the same domain and range. So just looking at the graph, what does it look like the domain is here? Remember, domain is what values can you use for x, right? So yeah, what numbers can you plug in for x in this formula, e to the x power? You can plug in any real number, right? So the domain is all real numbers. So that graph extends all the way to the left and all the way to the right along the x-axis. The domain is all real numbers. You can raise the base e, or any base for that matter, to any power x. Okay, positive or negative. It's possible to do that. What about the range? So what y values do you get here at the graph? What now? From 1, well, on the y-axis there, Jad, what portion of the y-axis do these curves cover? So what y-coordinates are you going to get? Yeah, from 0 to infinity, right? Yeah. So starting at 0 and going up to infinity, but not including 0, because you don't have any x-intercepts. It never touches the x-axis. So the range there is 0 to infinity. Domain, all real numbers, minus infinity to. See, remember, the reason you can plug any number in for x, so the reason the domain is all real numbers is, remember, you can do these calculations, e to a power, for any number you want to put in, right? E squared, of course, you can compute that, or e to the 10th power, you can compute that, right? What about e to the minus 2 power? You're wondering about negative inputs. Why do you have negative numbers in the domain? How is e to the minus 2 calculated? Well, what does a negative exponent do? Inverse, right? So this would be 1 over e squared, right? What about e to the 1/2 power? Why can we use fractions? Why do we have fractions in the domain? Yeah, this is square root of e, right? Okay, so see, you can use any number there as a power of e. So your domain is all real numbers. So this graph is a smooth unbroken curve. It doesn't have any holes in it. Entire x-axis is the domain. Now, what I'm really interested in, though, is in this picture, and you can sort of tell what I'm looking for here, is e to the x, that's always increasing, right? And so that means it has an inverse, because you're not going to have any repeated y values. So so e to the x has an inverse function. What's the graph going to look like? So that's why I drew in the this is kind of supposed to be a 45-degree line. So that's what I drew in the 45-degree line, right? So y'all did this on the test pretty good, actually. So what do? We take this and rotate it, right? Around this 45-degree line. So this point is 0, 1. So that's going to get rotated to 1, 0. So I know this point is on there. And then the rest of the curve, I'm just going to have to guess at here, but I think it looks something like this. So there's what the inverse function. So now I'm wondering, what is the inverse function? So what is the inverse function of e to the x? It's not e to the minus x, by the way, because that looks like this, and that's not. So that red curve is not the same as this curve, right? So these two things are not inverses. This is something different. Wow, what is that inverse function of to the x? Okay, well, it has a special name, guys. All right, and you may be familiar with this function, but you may not have thought about it before as being the inverse of e to the x. So we already sketched the graph, so I'm not going to do that again. So the inverse of e to the x is called the natural logarithm function. All right. So the natural exponential function, its inverse is the natural logarithm function. It doesn't have a formula, all right? So it doesn't have a nice formula, but it does have a name, okay? And there's the name for this function. So think of ln as being the name of a function. It's the name of, it's like f of x, right? Okay, it's the name of the inverse of the natural exponential function. So the ln is very helpful, except the letters are in the wrong order. This is almost an acronym. It's natural logarithm function. So this is kind of clumsy to read off a page. If you see this ln x, students always want to say ln, all right? Unfortunately, you have to read that as natural logarithm. Okay, right? I'll know what you mean if you say that. You'll know what you mean, right? But the proper terminology is natural logarithm function. All right, now this is an inverse function, right? This is an inverse function. So what does that mean? All right, if you write natural log of x equals y, so natural log of x equals the some number, what does that mean? That means that if you take e to the y power, you will get x. See, these functions are inverses of one another. So they flip the x and the y, right? So if e to the y is equal to x, that means natural log of x is equal to y. That's very important to remember, okay? In fact, if you can remember this fact, you'll go a long way toward getting natural log questions correct, all right? So remember, if natural log of x is equal to y, if natural log of x comes out to be some number y, that means if you take e and raise it to this power, you have to get x, all right? Because they're inverses of one another. Yeah, forgetting this fact is what causes students all sorts of grief when they're dealing with natural logarithms. So you want to remember this. Now I'll tell you what this means in just a moment. What I have sort of scribbled in there as a note. Let's see if we can find the important properties of natural log of x. Okay. So I think some of them we can just tell from the graph. So Y-intercept, let's look at the graph. What is, see, we scribbled the graph up here, right? Because we know it's the inverse. This curve is the inverse of e to the x. So this is the graph of natural log of x. So it's Y-intercept. Where does it cross the y-axis? It doesn't. Yeah, it does not cross y-axis. See, because this curve never crosses the x-axis, when you flip the x and y values, this curve is never going to cross the y-axis. Because the blue curve has no x-intercepts, the black curve here, the inverse, has no y-intercept. So no y-intercept. That means the domain starts where? Domain for natural log starts where? 0, but not including 0. Not including 0, and goes out to infinity. What's the x-intercept there? That's kind of easy to see. 1. Yeah, there it is, right? Okay. So no y-intercept, but x-intercept right? So it crosses the x-axis at 1. What's its, we already said its domain starts at 0, but not including 0, goes to infinity. The range is all real numbers, right? It's hard to see from this graph, but the range is actually all real numbers. This curve is going to continue, and it's going to actually keep going up. It goes up very slowly, but it will continue to increase. So eventually you'll have a range of all real numbers. The whole y-axis be included range of this function. Yeah, Emil? Oh, the sign-in sheet, yeah. Let's scribble those things in then. These things are helpful to remember. So the y-intercept there, that's easy. None. Does not cross the y-axis. Oh, where is it increasing and decreasing? Always increasing. No y-intercept, we discussed that, right? Okay. Domain and range. The domain is from 0 to infinity, not including 0. And the range is all real numbers. So minus infinity to infinity. Or that's the natural exponential function, which is the inverse of e to the x power. Any exponential function with any base has an inverse, okay? So remember I said this could, you could have bases other than e, right? For exponential functions, you can have base 2, you can have base 10, you can have really any number as base. The most popular ones are base 2 and base 10 and base e, but you can have any number as base here. Any exponential function will have an inverse. The way you label that inverse is log, short for logarithm, and then you put the b here, same as this base in the exponential function, right? And then, of course, this is your input quantity, right? So, for example, if you want to write down the inverse of the 2 to the x power, that's the binary exponential function, you would write that as log base 2. That's how you read that, log base 2 of x, log with that subscript of 2x. And again, the log is short for the word logarithm. We abbreviate this log base 2 also. You'll see that sometimes abbreviated as LG. That means it's like the TV brand, right? That means a binary logarithm. That's log base 2, the inverse of 2 to the x power. Also, of course, 10 to the x power, the common exponential function, it has an inverse function. The name of that inverse function is log base 10. You put a log with a subscript of 10 here. That means the inverse of 10 to the x power. That is often abbreviated to by dropping the base. So if you just see log written without a base on it, that means base 10. That's the inverse of 10 to the x power. So on your calculator, you will have an log key. That means log base 10, and you will have an ln key, right? Natural log key. That's log base e. That was my note up here that I didn't explain a moment ago. Ln of x, that is log base e. That's another way of writing ln of x. So, so for the most part, when we're working with logarithms, we'll be working with a natural logarithm. And so you want to use your ln key on the calculator, right? If you slip up and use the log key, remember that's a different function. That's the inverse of the common log function, right? And it's going to give you slightly different values. Let me show you. Log functions have many interesting properties. Log functions have many interesting properties, but and so we're going to talk about those properties because they're very useful properties. So these are properties that many other functions do not have, that log functions do have. But before we talk about those properties, let's get to how we're going to use log functions, okay? Because we're going to use them just like we did inverse trig functions to help us solve equations, right? Our primary application of inverse trig functions was helping us solve equations. That's also going to be our primary application of logarithmic functions, in particular the natural log function, be to help us solve equations. So let's look at this equation. E to the x equals 125. Okay, that's called an exponential equation because it involves the natural exponential function, right? And I'm trying to solve that equation for x. So you know when you solve an equation for x, right? You ultimately end up with, you know, a line like this, right? X equals to something, correct? And that something is the solution to the equation. You see the problem in getting from this equation to this equation, right? Is that here the x is in the exponent and here it's not, right? So you see the trick here is getting the x out of the exponent. How do we do that? That's the hard thing of solving exponential equations like this one. How do we get the x out of the exponent? There's no algebraic operation that will do that for you. You can't, or no arithmetic operation that you can use to get the x out of the exponent. All right, it's kind of stuck there. If you only know arithmetic, it's kind of stuck. All right, but see now this is where our knowledge of inverses is helpful, right? Because we know the inverse of the function e to the x, right? What's the inverse of the natural exponential function? It's the natural log function, ln, right? So just like we did with inverse trig functions, let's apply the natural log function to both sides of this equation. You don't really have to use the parentheses with the natural log. It's kind of like sine and cosine. You don't always have to use the parentheses with this function, but you can, all right? And sometimes it's necessary if you have an expression that's very complicated. 125 is not complicated, so I really don't need the parentheses around the 125. The reason we don't always use the parentheses is, again, the natural log function. That function has been around for a long time. Okay, that function was used before parentheses were used in mathematical notation. The natural log function was the first logarithmic function that was developed, right? Okay, not log base 10, not log base 2, is the natural logarithmic function. The person that did this, by the way, that first explored the natural logarithmic function, name is Napier, John Napier, and he extensively calculated this function. He extensively calculated this function in tables. They didn't have calculators, right? So he calculated the function and tabulated it so that people could read values of the natural log function off of the table. This development, that table, revolutionized math in Europe. Okay. In fact, it's what led to people using decimals. Before those log tables were developed, people did not use decimals. They knew decimals, but they didn't use them often in calculations. Okay. So this really had the development of the natural log function really had a profound influence on development of civilization. Now our calculators will do this for us very nicely. So you can use your calculator now. You don't need a table of values to compute natural log of 125. What does your calculator say that is, by the way? What now? 4.83? Okay, so approximately 4.83. Now, but what about the left-hand side? Natural log of e to the x. So what's that going to be? X, because these functions are inverses of one another, right? They cancel each other. So you end up with just x. See, that's the power of inverses. So there it is. We know that x is approximately, see how easy that was? 4.83, nothing to that, right? Okay. You can check it by trying your calculator, use your calculator to raise e to the 4.83 power and see if you get approximately 125, right? Okay. Let's try another one then. So now y'all know the trick. This is easy now. Okay. So suppose I want to solve this exponential equation. See, I've got that unknown x that I'm solving for. It's trapped in an exponent. See, that's a real inconvenient location. I need it out of the exponent, right? So that I can see what my solution is, correct? So what's the trick for getting it out of the exponent? Natural log, exactly. So we're going to apply natural log here to both sides. Now you might be saying, well, but that's not just x there. Right? That's 2x, and this is x plus 1. But when you apply the natural log, same thing happens. These are going to cancel each other. So you end up with 2x is equal x plus 1. And now you just have to solve that easy equation. 2x is equal to x plus 1. Oh, that's so easy. Isn't that x equals 1? I think so, right? So there's our easy solution to that equation, just x equals 1. Okay, well, that's our beginning examples of how we're going to be applying these this natural logarithmic function. It's the inverse of the natural exponential function, and so those functions work very nicely together in helping us solve equations. Okay. All right. So we've got a lot more examples of equations to solve, and I mentioned we want to go through these properties because the natural logarithmic functions, in fact, all logarithmic functions, obey some really nice properties that make them kind of unusually useful. Okay. Other functions don't obey these nice properties like logarithmic functions do. Okay, but we'll take that up next time. We're not. It's too late to start that today. We're not going to remember that until next time. I mean, for next time anyway. All right. So we'll stop there today, and got a homework due tonight, right? So don't forget about your. You've got that one last homework. Well, not last one. It's the last graphing homework, right? On trig function. So try to finish that if you haven't already. That was actually due last week, but I shifted it back. So got another. All right. Gonna stop here.